Okay, in today's video, I'm going to be exploring one of the most important concepts in statistics, which is the spread of data. So when we describe a dataset, knowing the average or the central tendency, whether that be the median, the mean, the mode, it simply isn't enough, right? The measures of central tendency tell you where the data clusters around, so it gives you an indication of central tendency, but it doesn't actually tell you the probabilities of any point landing within a certain range. All right, and this is where spread comes in. So in this example, we have two classes. We have class A and class B. You can just imagine these as two classes where people took a test and they both scored 75% on average. Now, if we look at the actual distribution of the grades using a histogram, we can see that class A had very low spread. Now, with this visual representation, it's easy to see what that spread means. Here we have values that kind of range from 70% up till around 80%, and it's all tightly clustered around our mean. Now, for class B, we have the opposite. We have the same mean, but the data is very far apart, right? So one very, I'm going to call it primitive, primitive measure of spread is to take the range. The range is simply looking at the minimum value and the maximum value, and then comparing how far apart they are. That tells you in a very simple manner how much spread there is to the data. The next one is the variance, which we love to use. It's very, very important. And I'll show you how we calculate that. So we'll go over here. So imagine we have this data set. We have 2, 4, 6, 8, and 10. First step you do is calculate the mean. And then for each point that we have here, you will subtract the mean from it, and then after that, for each of these points you square it, then you add them together, you take your sum, and you divide it by the number of values. Now, this denominator will change depending on whether or not you're using a sample or a population, and in almost all cases, you're studying a sample, because a population implies that you know all of the data for the people that you're studying, which almost never happens. In the case of a sample, it would be this minus 1. So this would be 4, and the variance would be 10. But anyways, in this case, we just assume that this is population data. So we have a variance of 8. Now, what does that tell us? Well, what we have here, so we look at the deviation from the mean. This is the subtraction, right? When we subtract that data point by the mean, how far away is it in terms of pure raw units? This one is negative 4 units. This one's positive 4 units from the mean. Positive 2, negative 2, 0. Sticks right at the mean. Now, with the variance, as we did before, we took that difference and then we squared it. So we see here that this value, data point 0 that we have over here, is 16 points squared from the mean. This one is 4 points squared. So you can see here, if we had more and more points that were further and further from the mean, we would have this nice parabola. And I can actually display that if we did, let's say, negative 2 or negative 3, whatever. We can even do negative 10. We can say 15, and then why not? We'll add 15, yeah, and then 20. Okay, so we're gonna run all of this, and then we will see we create this parabola as the points get further and further away, right? And this changes. So if you had a lot of data points, this would be a very nice squared line. And that's what variance looks at. Essentially, the further away you are, you have this quadratic relationship with the origin, the mean, which is very interesting. Okay, so now if we look over here, so we're going back to the example with the classes. If we take the square root of this variance, what we have is our standard deviation. The variance looks at the units but it squares them, right? So they're not very interpretable. Like here, this point right here is 250% squared away, points away from the average test score, or what? Well, this is not the same example, but imagine it was. This doesn't make any sense. You square it, and then suddenly you return to the normal land, to the land of the units that we used originally. So for class A, if we go back here, standard deviation is 2.71%, whereas with class B, it's 13.23, which is a lot more spread than class A, right? So if we talk about the standard deviation, we have to talk about the normal distribution. This is something that we see in a lot of data that we collect naturally. When we collect a lot of data points for a lot of things, there tends to be for all of these things that we collect, let's say it's car weights or emissions even, right? Emissions by countries or height or weight, pretty much hand sizes, bed costs. Like most of these things, when you look at enough data points, they tend to strangely follow a distribution that looks a bit like this, where we have our center with the mean over here, and then we have a lot of data that tends to be pretty close to the mean, and then as you move further away from it, there's a lower and lower probability of seeing, well, I guess in this case, if we're looking at a single data point, lower likelihood of seeing that specific data point. So, what does this mean? Well, with this normal distribution that we see everywhere, roughly, we have this rule, which is called the empirical rule, or the 68, 95, 99.7% rule. And it tells us that within one standard deviation, plus or minus, so one standard deviation above the mean and one standard deviation below the mean, we have a 68% chance of seeing that data point within it, right? Now, if we move to 2 standard deviations, at that point we cover 95% of the data. And by the time we reach 3 standard deviations, which is over here, we will see almost the entirety of the data. And then anything past that, we can consider them to be extreme outliers. So this applies all over, right? It's very interesting to see. And even, I haven't talked about other kinds of distributions because there are other kinds of distributions. But essentially, if you take a sample from any distribution, a sample of it, and then you calculate its mean of the data you sampled, and then you sample it again and again and again and again and again, you will always see a normal distribution. As per the law of large numbers and the central limit theorem, which will all be covered in other videos. So, empirical rule application. Well, if we go here, we see that 68% of students scored between 65 and 85, 95% of students scored between 55 and 95, and 99.7% of students scored between 45 and we'll say 100 because 105 doesn't make sense. This is for both classes. So that is one very important measure of spread, and you will see it again and again and again. And the standard deviation only applies to the normal distribution. Now you can approximate it to distributions which aren't exactly normal, right? You might have the data skewed a bit more on this side, or slightly heavier tails, as we see with the t-distribution, which is also just a normal distribution, but anyways. But for something like an exponential distribution, where we have a curve like this, looking at very unlikely events, not so much. So, Now we look at another measure of spread called the interquartile range. So standard deviation, variance, those use the mean as the central point of the calculation, right? You need to subtract the mean from every data point to reach those values. Now with the interquartile range, what you do instead is you use the median. So you cut the data in half, and then you cut both, and so now you have two splits, right? You have the lower split and the above split by the median. And then within those two, you also split those in half, once again looking at the median of those, and then you create these quarters. So you have quarter one, you have the median, and then quarter three. And the interquartile range is simply looking at the difference between quarter three and quarter one. So in this case, we have what's called a box plot, which, as mentioned over here, looks at Q1 right here, and then Q3 up here, and then we have the median over here. And when we compare the spreads of the data, right, for class A and class B, the box plot, similarly to variance and standard deviation, can give us a good indication of how spread out it is. For class A, we can see here that the data is much more compact. The vast majority of the test scores fall within 70 and 80%, with one outlier over here. Whereas class B, I mean, wow, it really can be anywhere, right? We don't know where a point will land because there's just so much more variance to it. So interquartile range, it tells you the story of how your data is distributed around the center as well. And using both can give you a good way to quantify exactly how different these two distributions might be. And it just gives you a good idea of the spread in your data. So over here, we're looking at, yet again, this is interquartile range versus standard deviation, handling outliers. So we create data with normal distribution, add outliers, okay. And yeah, without outliers, you can see that the IQR is pretty good. Well, actually, the IQR here is about the same for both because it uses a median, which is robust to those outliers. But you can see here that, like if we were to use the standard deviation, it would be quite moved by these guys. As you can see here, with the outliers, standard deviation is 21.29. It's an increase by a lot without the outliers, whereas the IQR is robust to those. So if you have a distribution that has significant outliers in it, IQR, I would always use IQR and the standard deviation anyways, just for analysis of your data, but it gives you a good indication, right? And then using IQR, you could decide where to trim the mean and to do all of that. Same with mean and median, just use both. They're easy to calculate, so it gives you a good idea. Anyways, that's the video. Thank you for listening, and there will be more on spread of data, variance, all these things. They are super important statistics. Thank you.